video, we're going to talk about 1.1 again. We're going to talk about examples 6 through 10. Now, the main reason for studying algebra throughout the ages has been to solve equations. We develop algebraic models for phenomena so that we can solve problems, and the solutions to the problems usually come down to finding solutions of algebraic equations. If we are fortunate enough to be solving an equation in a single variable, we might proceed as in the following example. So we solve this algebraically. Here's how it goes. First things first, we need to get everything to one side. Once we do that, we can notice that there's an x in every single term. Now we should see that we have 6 times negative 10 is negative 60. 2 factors of negative 60 that give you negative 11 would be negative 15 and positive 4. So we're going to continue factoring. Now the only way we're going to be able to get 15 or negative 15 is by using 3 from this 6x squared. So we use 3x and 2x. Now the only way we're going to get 15 is if we use a negative 5. The only way we're going to get 10 is if we get a positive 2 here. Negative 15 plus 4 is negative 11.
Just don't close the door.
Now when we solve this for the zero factor property, here's what we're going to have. Our x equals 0, 3x plus 2 is equal to 0, and 2x minus 5 is equal to 0. Which means, again, x will be 0, x equal negative 2/3, and x will equal 5/2. Now it does say to solve it graphically. So what we're going to do here, in for y equals, we're going to put in 6x cubed into our first y equals, and 11x squared plus 10x into y2. And then since it looks a little jumbled by the origin, I'm going to zoom in one time. There's our answers right there. Our first answer, if we go intersect, there's negative 2/3 right there. Our second intersection, there's 0. Now for our third intersection, we're going to have to go to the right a little bit. We're going to make our y max, let's just make it 15 just for kicks here. So I'm going to have to make the y value a little bigger. There's our intersection at 2.5. Now for part B, we're going to have to do a lot of the same stuff. We'll have 2x squared minus 5x plus 2 on the left side. And when you FOIL this out, we'll have x squared minus 5x plus 6 plus 3x on the right. Well, you should see that the 5x's will go away because they're the same on both sides of the equal sign. I'll bring the x squared over, I'll bring the 3x over, I'll bring the 4 over, so I'll go with x squared minus 3x minus 4 is equal to 0. If you were to factor this, we have x minus 4 and x plus 1 equal to 0, which means x will equal 4, x will equal negative 1. There's your answers. So again, if we were to graph this, I'll solve it by using these here. So we'll have 2x squared minus 5x plus 2. We'll have x minus 3, x minus 2, plus 3x. Change our y window a little bit here. Again, we'll find intersection points. There's our first intersection point of x equals -1. And our second intersection point of 4. Now, one thing I do want to point out with the calculator, if you want to go intersection, and you have, say, 3 curves on it, and you want to find the intersection between one graph and another graph, you can switch between graphs by pressing the up button or the down button. You'll see that they switch in the top left corner. That will tell you which curves you want to work with. Now in example 6, we use the important zero-factor property of real numbers. A product of real numbers is 0 if and only if at least one of the factors in the product is 0. You've been using this again and again since algebra. Now it's this property that algebra students use to solve equations in which an expression is set equal to 0. Modern problem solvers are fortunate to have an alternative way to find such solutions. If we graph the expression, then the x-intercepts of the graph of the expression will be the values for which the expression equals 0. We'll be doing a lot of the same stuff here in example 7. Again, first, let's move everything to the left side. Now you should notice there are no 2 factors of 10 that give us 4. So I'm going to have to complete the square here. Half of 4 is 2. Add that to both sides, the 2 squared, which means we'll have x plus 2 quantity squared equals 14. Solving this for x, we'll take the square root first, and then we'll subtract 2. So there's your zeros. Now if I were to graph this, what we can do, we can take x squared here, and we can take 10 minus 4x in the second one. I'm going to do this a little bit differently than I did before. We want to find the intersections. Now, if I press second calculate, I want to find a value. I'm going to press enter on that. And you'll see x equals on the bottom left there. -2 plus the square root of 14. Is right there, 1.74. And you'll notice if you press the down button, you're switching between the equations. It's the same exact point. Now if you go -2 minus the square root of 14, again, you do the same thing, you get the same exact answer each time. So that truly is your answer. Now when we look at B, we'll have to distribute the x first and bring the 14 over. Now there are no 2 factors of 14 that give us 7. So again, we're going to have to complete the square. Take the 14 back. Half of 7 is 7 over 2. So when you factor, we'll have x plus 7 over 2 squared. Now we're going to do -14 plus 7/2 squared. Oops, it should be, sorry, positive 14, not negative. So we'll have this. You're going to get 26.25, or if you press math, enter, enter, you get 105 divided by 4. We're going to take the square root of both sides. When we do some simplifying, you'll get this, which means x will equal a negative 7/2 plus or minus the square root of 105 over 2. Now, when you put these into your calculator, we'll have x squared plus 7x minus 14. And if we put in value again, negative 7 divided by 2 plus the square root of 105 divided by 2, get an answer there. And then negative 7/2 minus the square root, 105 divided by 2, you get your answer there. Now, we use the graphing utility of the calculator to solve graphically in example 7. Most calculators also have solvers that would enable us to solve numerically for the same decimal approximations without considering the graph. Some calculators have computer algebra systems that will solve numerically to produce exact answers in certain cases. In this text, we will distinguish between these two technological methods and the traditional paper and pencil methods to solve algebraically. Now, the calculator that they're talking about is the TI-89 and the TI-92, which is exactly why those aren't allowed on the ACT. Now, every method of solving an equation usually comes down to finding where an expression equals 0. If we use f of x to denote an algebraic expression of the variable x, the connections are as follows. If a is a real number that solves the equation f of x equals 0, then these three statements are equivalent. The number a is a root or a solution of the equation f of x equals 0. The number a is a 0 of y equals f of x. Also, the number a is an x-intercept of the graph of y equals f of x. Sometimes the point a0 is referred to as an x-intercept. Please keep these in mind, this fundamental connection. You'll see them in the directions again and again in different ways. Now, moving on to problem solving. George Polya is sometimes called the father of modern problem solving, not only because he was good at it, but also because he published the most famous analysis of the problem solving process, how to solve it, a new aspect of mathematical method. His 4 steps are well known to most mathematicians. 1, understand the problem. 2, devise a plan. 3, carry out the plan. And 4, look back and check. Now, the problem-solving process that we recommend you use throughout this course is the following version of Polya's 4 steps. Step 1, understand the problem. Step 2, develop a mathematical model of the problem. Step 3, solve the mathematical model and support or confirm the solution. Step 4, interpret the solution in the problem setting. So basically the last part means translate your mathematical result in the problem setting and decide whether the result makes sense. Now, in example 8. The engineers in an auto manufacturer pay students 8 cents per mile plus $25 per day to road test their new vehicles. How much did the auto manufacturer pay Sally to drive 440 miles in 1 day? So here, to understand the problem, we want to know how much Sally's going to get paid. Well, we're going to let x equal the number of miles. So really what we're going to have here P will equal 0.08 times 440 plus the $25. So the 440 here, this is where the x are going to go if we're just going to create an equation. Now, all we do, we throw it into our calculator. 0.08 times 440 plus $25. So Sally made $60.20. And if you look at it, the calculator said 60.2, but because I knew it was money, that's why I made it 0.20. Now, if you look at B, it says John earned $93 test driving a new car in one day. How far did he drive? Well, the 93 will go here, 0.08 times x for the number of miles plus 25. Well, to solve this, we'll subtract 93 and 25. We'll get 68. Now to solve for x, we're going to divide that number by 0.08. He drove 850 miles. That's how far John drove. Moving on to letter B. Swan Auto Rental charges $32 a day plus 18 cents per mile for car rental. Elaine rented a car one day and she drove 83 miles. How much did she pay? Well, the cost was 0.18 cents per mile times 83 miles plus 32. So she paid $46.94. Now in part B, it says Ramon paid $69.80 to rent a car for one day. How far did he drive? Well, the cost, $69.80. We go 0.18 times x plus 32. We're going to subtract $69.80 minus 32. We're going to divide that by 0.18. He drove 210 miles. Now, it is not really necessary to show written support as part of an algebraic solution, but it is good practice to support your answers wherever possible simply to reduce the chance for error. We'll often show written support of our solutions in the book in order to highlight the connections made among the algebraic, graphical, and numerical models. Now, next one we're going to talk about is grapher failure and hidden behavior. Now with your calculators, you won't see too much grapher failure. That is generally on the TI-83 pluses, you'll see grapher failure. You won't see it on the TI-84 pluses, which is exactly what you all have at this time. So we're going to actually skip example 9. Technically, there is no x-intercept on the TI-83 plus. You'll see an asymptote line there, which looks like an x-intercept, but technically it's not an x-intercept. That again, that was on the older version of the same calculator that you have. Now, if you look at B, it says look at the graph of y equals x to the 200 to the 1 over 200 power. Well, if we do this, what we'll have, you should know when you multiply your powers, you'll get y equals x. Okay, for all x greater than or equal to 0. Now, if we were to graph this equation, in the window 0 to 1, this is what it's going to look like. The problem is Your calculator, it says here, graph equations, you did, is a graph different than y equals x? Well, the problem is, when your calculator is graphing these, it's taking each value of x, plugging into the equation, coming up with a dot for y. That's why it took so long to figure out for the calculator. It's not going to graph y equals x because what happens is, the value between, in the empty space here, is so small your calculator can't figure it out. That's why there is that empty space there. So there's your explanation why the graph failed. Now moving on to 10, not seeing hidden behavior. Solving graphically, find all real solutions of the following equations. Watch out for hidden behavior. Well, let's plug these in. Okay, it looks to me like there's going to be just two solutions. Obviously, -9 will be a 0. So we'll go look at that one quick. Zero is at -9. Now, if we do this again, you have to be careful when you look at around 5. So what I'm going to do, I'm going to zoom in. I'm going to zoom in again, just to show you what's really happening. You can see that there's actually going to be a dip there. So we'll have to find those two zeros also. This is what they mean by hidden behavior. So we'll have 1 0 at 5. And your other 0 will be at 5.1. So there's your 3 zeros. What looked like there was going to be 2 zeros here actually turns out to be 3 zeros. Okay? That's why you have to be careful for not seeing hidden behavior. Let's try the next one. Again, same type of thing. It looks like there's going to be a 0 at -3. And you can see that there is going to be one. But if we look for zeros here, you can see that it doesn't look like it goes below the x-axis there. Okay? So there's, we have one more 0, 1.15. Let's zoom in again. Let's kind of take a look. We'll zoom in one more time just to get a better look at it, you can see it does definitely dip below twice. So 1.1 is a 0. And also 1.15. So our zeros would be those are your 3 zeros. Now, if you should have any questions, please talk to Lainey and Alex. They would have all the answers.